Good morning, everyone. I just wanted to make a video here just going over how to find the quadratic and linear and then later on exponential models of given a relation. So I figured I would do this by doing one of the questions that's assigned for homework. So it is on page 191, number 6. So I'm just going to show you how we can use technology to find the quadratic model, and then just so you know that it'll have a similar format for other questions like this. So it is on page 291, number 6. So this is one of the questions that I assigned here. So I just kind of wanted to go over just how to use technology to find the graph, to find the equation of the model, and also how to interpret different parts of it. So the first part of this quote, well, I'll read the question here. So it says, an Acme Container Company makes cylindrical plastic storage containers with a fixed height of 1.5 meters. The radius of each container and its volume are shown in the table. So the first thing it says, calculate the finite differences and to determine whether it's linear or quadratic. You can definitely do that first part without technology, right? So all we're doing in that case is simply finding out what the first difference is, and then we're going to find the second difference. So I'll let you do that on your own. It's pretty easy. You don't need technology for that. Then when it says if the rate of change of the volume with respect to radius is increasing, decreasing, or constant, again, that's you looking at the first and second differences and seeing if you notice, just looking at the first differences and seeing if they are increasing or decreasing or staying the same. For part C, this is where we get to the meat and bones here. We're going to be using technology to graph out, first of all, graph out this this relation, and then we're going to be also on Desmos. You can kind of do it in one step. You can find the graph and find the quadratic model as well. So what I'm going to do first is I'm going to insert all the information. So I go to the plus sign here, and then I click on table. And what I'm going to do is I'm simply going to write in the x values and the y values here. So I have a radius in this case is my x value, and then my y value is the volume. So I'm going to write 50 and 1.18. So I'm just kind of looking back and forth here. Then I have 75 and 2.65. And where am I getting all these numbers from? Again, this is just on page 291, number 6. All this is given to me. All I simply need to do is put this on the graph there. And I have 104.71. You should be able to calculate, by the way, what the volume and the radius is just by working backwards, right? Going back to our unit on geometry. But for now, let's just focus on the actual table here. So we have 107.36, and finally our last one here is 150 and 10.6. Okay. So one thing you're going to notice, if you're looking at this and you're like, I don't see a graph, it's because you need to zoom out, right? These values are not going to be seen here because it's too small, and you can actually see here that our x values actually start at 50. So now we see our first value, right? Once we start zooming out. So there's a whole graph. So you have a couple options. I personally don't like zooming out too much because then you really can't see much of a change, and you can't see much of a relation there. So what I would suggest is switching your x and y axis, like the settings for your axis here. So you go to the little wrench tool here, and you're going to simply select, in this case, our x went from 50 to 150. So we don't need negative numbers. So let's say that we go from 100 to, what's the highest value, 150. Let's just say we go to 200, right? That should give us a better graph of what the graph looks like. And for steps, you can specify if you want to go up by tens, by ones. Might be easier to go by tens, just so you can see everything there. I always personally get rid of this, the minor grid lines. I just find it a little bit confusing. You don't have to get rid of it. It just sometimes it does kind of throw students off. You can keep it for now. In this case, like I said, it's totally optional. Just some students prefer to just get rid of that. Sometimes they don't want to have too many lines on there. And then for your y-axis, so I can see here for my y, I go from 1.18 to 10.6. So first of all, I don't have any negative numbers, so I might as well just go from 0 to let's be safe here. Let's say 15, right? And of course, these numbers are quite small and they're not changing by much. So maybe the steps, I'll make them a little bit smaller. Maybe I'll go up by ones. And I think that should give me a decent view of what's going on here. So hopefully that's kind of clear what this graph looks like. We actually can notice that it almost looks like it could be linear, but we're not 100% sure. But to be safe in this question, they wanted us to find an equation that models this, and we could try a linear model, just so you know. So let's actually do that because we know how to do the linear model. So all we're going to do is on the second line, you're going to type in y1, and then you put the squiggly line is equal to mx1 plus b. And remember, all these equations, if you're looking at this and you're still wondering how did I know that, all these equations are just in the handout there for you, okay? And I've given you all the commands, so all you need to do is just type them in. But I'm just showing you, I guess I was going to say in person, but it's not in person, but I'm showing you on a video how to actually go through it. So we can see here that our linear, our line of best fit is this line right here, and our equation, we can find it by looking at the m and the b value. Now, this looks fine, but to be honest with you, it probably isn't the best model that we can have for it. So let's try to see if we can get a quadratic model. And the reason I'm specifically asking for a quadratic one, because in this unit, in this section, we're learning about quadratic models. So I'm actually going to ask you to find the quadratic model here. I'm just going to move this a little bit. You can see it a little better. So I'm actually going to delete this. So if you ever want to delete something on Desmos, you can just press X. And I would definitely, the other option too is you can also, I forgot to do this here. I just want to show you how to do this. You could also highlight the actual color of it, and then it actually just blanks it out. So if you ever just want to temporarily get rid of something, you don't want to just want to hide it, you don't actually want to delete it, you can always just click on the color there. So I'm going to go to the second command line here, and I'm going to type in y1. So now I'm going to be doing the quadratic model. So I'm going to type in y1 is approximately equal to ax1. And now when I do the square, be careful with this. On your laptop, it's a lot easier because you can use the little hat symbol, it's the upward arrow, this one, the chapeau in French, right? You can use that one if you want to try to add in an exponent. If you have your phone, that's what most of you will have here. On your keyboard, you're actually going to be typing in this little symbol right here, a squared, and basically what it does is it just squares whatever your variable is there. And then we're going to write plus bx1. And again, the 1 there is really important, right? Because we're simply telling Desmos to take the x variables here, but they're not labeled as x, they're labeled as x1. And then we write plus c. And we are done. And actually, you can see here that this is a perfectly quadratic model, right? So even though the linear one seemed like a good approximation, this is even better. It's actually perfect. R squared value is 1. And we learned about R squared value in the last unit. So we can see here that this would be our quadratic model. So how do you actually find the equation? So that's before now we're moving on to part D here. It says find the equation. For part C, it says determine the equation, and then for part D, we're going to be using the equation. So I'm just going to finish off part C here. So for part C, what is our equation? Well, our A value is 0.000472. So that's going to be x squared. And then we normally would write plus bx, but in this case, we're going to be subtracting because it's negative. So minus 0.002 x, and then of course, the final value is plus 0.01. And that's our equation of the quadratic model. For part D, it says use your equation in part C to predict the volume of the container with a radius of 180 centimeters. So 180 centimeters is going to be our radius. And we actually know this from the question. We were told that the radius is the independent variable. It's the x value. So that means that our radius or our x value is going to be 180. So what we need to do in this case is simply take 180 and sub it into x. So every single time you see 180, we're not going to write, every time we see x, we're not going to write x anymore. We're going to write 180. We're simply going to be substituting it in. So that means that we take 180 and we square it times 0.000472. minus 0.002 times 180 plus 0.01. And I'm not going to do the whole math there for you. I'm going to hope, fingers crossed, that you guys are okay with at least the substitution and, going through BEDMAS and then solving that equation. I'm hoping that's fine for you. I just wanted to kind of show you how you use technology to come up with the equation, then use the equation. And then for part E, we're going to keep going with the graph here. It says draw the graph with the radius. Well, we already talked about this radius on the horizontal axis and the volume on the vertical axis. Does this shape show that it's quadratic? And absolutely it does. We can see it's quadratic. It doesn't even, it's sometimes it just throws people off because it almost looks like it's exponential. But if you zoom out of this graph a little bit, you can clearly see that it is quadratic, right? It's parabolic in nature. And we definitely have vertex, and and this is what throws people off sometimes, right? It doesn't look like it's it might look like it's exponential, and we'll talk about exponential graphs later, but it definitely is quadratic, especially if you zoom out of this graph. You can definitely see that very clearly. And then for part F is a little bit more complicated. It says use the graph to estimate the radius of a container with a volume of 6 meters cubed. Again, if you do not have technology, this question definitely can be difficult, but we are given technology. So if we are given technology, what you're going to do is you're simply going to find out when the volume or the y value is equal to 6. So here's 6, and what I'm going to do is go all the way across here and just estimate what the x value would be. So my x value would be between 110 and 120. So I'm going to take a guess here, 112 or so, right? So it's somewhere in between. So I would say 112 would be our best estimate for the radius. For in this case, that would give us the volume of 6 meters cubed. So if you want to actually find the exact value, again, Desmos is awesome for this. I'm going to clear the drawing just so you can see it more clearly. There is another little tool you can use. Let's say that you want to find out, you're really trying to figure out when does this quadratic graph here, when is it equal to 6? So if you want to find that, we know in this case that we want y to be equal to 6. So we're simply going to draw a line that is y is equal to 6. And we are simply trying to find out when are they intersecting with each other. And I can actually see here that they intersect at 112.865 and as an x value and 6 as a y value. So this is my point of intersection, and that's actually extremely close to what I had estimated. I said that it was going to be 112. It was 112.865. So that's pretty good. And this is the exact so now we can see here that this is the exact radius, 112.865 centimeters, sorry, that would give us a volume of 6 meters cubed. So I hope that kind of helped you. Just like I said, just that question was just to kind of show you how to use technology, to graph it, to find the equation, and then of course to interpret the equation. So hopefully that makes it a little bit easier. All right, best of luck.